my name is Muhammad Shami, and today we're going to do a presentation about MAT575 Perimeter of Tasik Section 7. And this presentation is going to be presented by Group 6. Our team members consist of 4 people. First one we have Nicole, and then the second one we have Donita, and then the third one we have Alia Razmi, and then lastly me, Muhammad Shahmi. So now let's move on to the introduction. Tasik Section 7 has an uneven and irregular boundary, making its perimeter difficult to determine using basic geometric formulas. This project aims to estimate the total perimeter of the lake by using coordinate points obtained from a scale sketch of its boundary. The study also demonstrates how mathematical and numerical method can be applied to real-world geographical features to obtain approximate and more accurate perimeter of the measurement.
Now, for the literature review, we first studied on the characteristics of Tasik Section 7. Tasik Section 7 is an artificial lake that is mainly used for recreational activities and water storage. However, because the shape of the lake boundary is irregular, the perimeter is difficult to be calculated accurately using basic geometric formulas such as circles. Therefore, numerical methods were used to estimate the perimeter of the lake based on coordinate points obtained from a scaled map. In this project, Newton's forward-divided difference interpolation method was applied to approximate the boundary curve by forming a polynomial equations from the coordinate data collected. After obtaining the equations, the perimeter was estimated by calculating the total arc length along the interpolated boundary curve. Besides that, we also understood that the results obtained are only approximate because errors may occur during interpolation, map sketching, scaling, and rounding process. Finally, the string and ruler method can also be used as a comparison method to estimate the perimeter and determine the percentage error between both methods. This shows how numerical analysis and calculus can be applied in solving real-world geographical problems.
Have you ever wondered how the actual perimeter of an irregular shaped lake is measured? Take Tasik Section 7 as our case study. Because the lake boundary curves unpredictably, simple geometric formulas like those for circles or ellipses cannot provide accurate result. So how do we solve this? Our approach begins by extracting coordinates points from a scale map of the lake. Then we apply Newton forward divided difference interpolation method to derive polynomial equation that fits each section of the lake boundaries. Once we have these functions, we can use the calculus arc length formula to accurately approximate the total perimeter of the lake, demonstrating how numerical analysis tackles and world challenges.
Okay, so now we move on to methodology. So the methodology, first thing we did was we did a data collection using a Google map, and we also did data collection by visiting the site itself. And then the second step we did was divided difference table. And then the third one we did is an interpolation polynomial, which is the formula we put here. And then the fourth step we did was perimeter estimation, which is L equals to integration of a to b cert 1 plus dy dx power of 2 dx. And then the fifth step is exact perimeter, or we use a manual, or we call it map measurement method. And then the sixth step is unit conversion. And then lastly, we did an error analysis of the project itself.
Next, I will present the result obtained from the perimeter approximation of the lake. First, the image of the lake was taken from Google Maps and traced onto graph paper. The boundary of the lake was then plotted using coordinate points to represent the shape of the lake more accurately. After plotting the graph, the lake boundary was divided into 4 quadrants to simplify the approximation process. For each quadrant, the coordinate values and the related terms such as x squared, x cubed, x to the power of 4xy, and x squared y were calculated and tabulated. These values were used later in the least square quadratic approximation method to form the normal equation for each sections of the lake. The graph shown on the right represents the plotted lake boundary together with the selected coordinate points and quadrant divisions used throughout the analysis process. For the analysis part, the least squares quadratic approximation method was applied to estimate the boundary curve of the lake. The boundary was divided into 4 quadrants so that each section could be approximated more accurately using separate quadratic functions. For quadrant 1, the required values such as x, y, x squared, x cubed, and x to the power of 4xy and x squared y were first calculated and arranged into a matrix normal equation. The general quadratic equation used is fx equals to a0 plus a1x plus a2x squared. Using the summation values obtained from the table, the metric equation was formed and solved using the Gauss elimination method. The elimination process was carried out step by step to determine the coefficients a0, a1, and a2. After solving the matrix, the coefficients obtained for quadrant 1 were a0 equals to negative 5.006, a1 equals to 8.036, a2 equals to negative 2.136. Thus, the quadratic equations for quadrant 1 became f1x equals to negative 5.006 plus 8.036x minus 2.136x squared. Next, differentiation was performed to obtain the derivative of the function. f1 prime x equals to 8.036 minus 4.272x. The same procedure was then applied to quadrants 2, 3, and 4 to obtain the remaining quadratic equations.
Moving on to the analysis phase where the actual mathematical computation take place. To make the analysis manageable, we divide the lake boundary into 4 sections. So for each section, there will be quadrant 1, 2, 3, and 4. For each quadrant, the arc length is calculated using the standard calculus formula, which is L is equal to integrate BA square root 1 plus fx square dx. So for quadrant 1, after we got the fx and f prime x, we will substitute the derivation into the arc length formula, setting by the integration limits from x equals to 1.9 to x 2.3. Solving this integral yields of an arc length of L1 is equal to 5.6232 units. And moving on to quadrant 2, we derive the represent f prime x is equal to negative 6.074 plus 1.5x. So by integrating this, the x limits is x equal to 2.2 until x equal to 4.4. So we get the arc length equals to 1.3306 units. For quadrant 3, we return to the function of fx. After finding its derivative, we plug into the formula and evaluate it within the boundaries, which is x equal to 2.5 equals and x equals to 4.4. This calculation result obtain L equals to 2.5849 units. And lastly, for quadrant 4, we have the function of fx yielding a derivative of f prime x equal to negative 1.242 plus 0.912x by integrating from x equal to 1.9 until 3.3 give us the final segment length of 5.3753 units.
For the final analysis, All arc length obtained from each quadrant were then added together to estimate the total perimeter. The sum of all sections gave a total length of approximately 18.214 units. Next, we converted the result using the selected scale, where 1 centimeters represents 100 meters. Therefore, the estimated actual perimeter is approximately 1,821.4 meters. The final results show how interpolation and calculus can be applied to estimate the perimeter of an irregular shape more systematically. In conclusion, this project successfully demonstrated the application of numerical methods in estimating the perimeter of an irregular shaped lake. By using coordinate points, interpolation techniques, least square approximation, and the arc length formula, we were able to estimate the perimeter of Tasik Section 7 more systematically and more accurately. This project also helped us to understand the practical application of calculus and numerical analysis in solving a real-world problem. Although the result is only an approximation, this method provides a reliable estimation compared to basic geometric methods. Overall, this project improved our understanding on mathematical modeling and numerical computation.
Okay, that's all from us. Thank you for watching our group project video. Goodbye.